In some occasions, we will work with several random processes at the same time. In this case, we talk about multiple random processes or multidimensional random processes. In this video, we will extend the concepts of independence and correlation and stationarity to several random processes. And we will start with the concepts of independence and correlation. Two random processes, x of t and y of t, are independent when the random variables that we get when we evaluate x at a given time instant t1 and y at another time instant t2 are two independent random variables. And similarly, x and y are uncorrelated when these random variables are uncorrelated. It is convenient here to remember when some random variables are independent or uncorrelated. The definition of independence is related with the conditional probability density functions, with the conditional distributions. And by definition, two random variables are independent when the conditional distributions, the distribution of y given x or the distribution of x given I, are equal to the marginal distributions, to the distribution of y or the distribution of x respectively. To know the result of a given random variable doesn't change the prior statistics about the other random variable. This is the definition of statistical independence. As an implication for statistically independent random variables, the joint distribution, the joint probability density function, is obtained by the product of the marginal distributions, the distribution of x times the distribution of y. The definition of uncorrelation is related with the correlation coefficient, and the correlation coefficient was the normalized version of the covariance between two random variables x and y. By definition, two random variables x and y are uncorrelated when its correlation coefficient is equal to 0. And independence in general is a constraint that is much more strong than uncorrelation. Independence implies uncorrelation, but uncorrelation doesn't imply independence necessarily. The exception are jointly Gaussian random variables. In this case, uncorrelation and independence are totally equivalent, but only for these random variables. Therefore, two random processes, x and y, are independent when for every pair of time instants t1 and t2, the random variables x at t1 and y and t2 are independent. This means that the conditional distributions are equal to the marginal distributions, and they are uncorrelated when for every pair of time instants these random variables are uncorrelated. Their correlation coefficient, their covariance, is equal to 0. When we have two random processes, the cross-correlation function is a natural extension of the definition of the autocorrelation function for a single random process. The cross-correlation function between x and y evaluated at two time instants t1 and t2 is the expected value of x at t1 and y at t2. If y is a complex random process, y is complex conjugated. Taking into account this definition, it's straightforward to see that if we have the cross-correlation between x and y, there is an evident relationship with the cross-correlation between y and x. We have the complex conjugation in the case of complex random processes, and we need to invert the order of the arguments. With this definition of the cross-correlation function, now we can extend the concept of stationarity. Two random processes are jointly stationary if, first, each one of them is stationary. This means that the mean is a constant and the autocorrelation function depends only on the separation between the two time arguments. And the second condition is that the cross-correlation between the two random processes will depend also only on the separation between the two time arguments. It doesn't depend specifically on T1 and T2, but only on its difference. Using the alternative notation, if we parameterize the two time instants as two instants with a separation tau seconds, the result will depend only on tau and will not depend on the specific time value t.